Next speaker will be Lucia Moura from University of Ottawa. She'll talk about new families of strength 3 over arrays using LFSR.
Thank you. And this little test that I know how to click. See, no picture.
Lucia, we were all expecting the nice pictures, huh? From you.
Oh, my. Get distracted and I won't speak. Okay. Okay, so I will be talking about new families of strength 3 covering arrays using LFSR, linear feedback shift registered frequencies from finite fields. This specific work that is in the abstract is joint work with my PhD student, KIANOOSH. I chose this topic because this topic of looking at LFSR sequence came about from my first joint work with Daniel, Brad, and Stephen. When around 2005-06, he showed us, oh, I found this paper by Munemasa, and it's talking about polynomials on finite fields, and it's to find orthogonal arrays. Brett and I were working covering arrays, orthogonal arrays, and I said, maybe we can do something. And that's how my story with this topic started. And also, it's something I'm working until now, because this was a paper that I said it was submitted when I submitted the abstract, but now we just got news that it was accepted, my modification. So it's something I have been doing for since then, So here we go. Up. So that's the script of the talk. This is just one slide, don't worry, I'm going slow. But please, can you tell me about when I'm at 15 minutes, so I know that I have only 10 more. So I will talk first about the introduction about LFSRs, or how to build a orthogonal array for LFSR. Thanks, Kirsten, and thanks both Kirsten and Andrea, because several definitions are going to repeat, so people are going to get more, they already have some intuition and understanding of those. So we're going to talk about this, then I will talk about how to use this to build some covering arrays. This is a result of 2014 with Raaphorst. Then I'll talk about the present work. And in the middle, there may be some things that Daniel did. But not a lot. But we just submitted this area, and we did that nice paper that had the approval case analysis of 375 cases that we divided between the costs. 72 pages that were not published, but was put in the archive to say that all these cases work and the result. It wasn't approved from the book, but nonetheless it was approved. Oops. Oh. Daniel, when I met him, this makes May 88. That's when I met him in 89, I think. No, 88 maybe. This is a renewal of your card, because we started in 87. The graduate program at the University of São Paulo. Full name, for the ones that don't know.
Thank you.
Daniel. He likes to hide this as he likes to hide his age, but now the cat is out of the box.
So, but are you sure this is not Lula? At the time, Lula at the time.
Okay, so as I was telling you, that is this important joint work, but I'd like to also mention my main collaboration, my three most important collaborations with Daniel, with you guys. Some of them you saw in smaller sizes in some of the pictures, Nathan, 33, Diego 20, and Lucas on the back there, the corner, 56. But now let's go to less important joint work, but the first, which is when we were outside. Yes. Oh, I want a point and I'm clicking. So this will happen. So he said, take a look at this paper. This was around 2005, maybe when we started this. This was published at this age, but
Actually, I saw the paper when it came out in FFA, and I thought, oh, this is a great idea, but I was working on something else. Maybe I come back one day, and I forgot about it. And then I saw it again in 2002.
Mhm.
And then I grabbed Brett, and you say, well, and no one, you know, no one cared about what I was saying, I guess. And eventually, like in 2004, you and Brett said, yeah, we should work on this.
Yeah, so orthogonal arrays, primitive trinomials and shift register sequences. So it was about trinomials, not dividing trinomials, and some conditions for then these giving orthogonal arrays. These orthogonal arrays are strength 2 and almost strength 3. Okay, so this is the first joint work. Doer, I couldn't find his picture on the web, but I could find that he published a book on problems in the theory of modular forms. Now, he changed, but at this time he was an undergraduate at Carleton, and then we got this problem to work. And, you know, the generalization was to consider pentanomials not divisible by trinomials, for example. Okay, after that, Daniel, Stephen, and another student generalized, because this was for F2, generalized for F3. Then comes this other work, which was Brett Stevens, that we've seen a lot. We've seen a lot of his papers as well. And our joint student, Sebastian Raaphorst, then we have this result here, which will be important for this talk, which is constructing strength 3 cover arrays from 2 almost strength 3 orthogonal arrays. And this gives you plots. We try to extend for 4 with Xanakis, a Greek student of Daniel. We had some interesting results in this paper, but they were more computational. We were trying to find what's, you know, how we can do similar things the best we can do, use a backtracking to see how large it could be the number of columns of these arrays that comes from pasting 2 orthogonal arrays coming from LFSR. Then came my first Brazilian student that just came, gave a talk, André Castoldi, came to Otto, and in various meetings, including some in our basement, we came up with something to a related object called order orthogonal arrays, and we also use the same machinery with the LFSRs. I won't talk about all of this. I will focus on some things here. Something else, character sums for Colbourn arrays,
Existence of Colbourn arrays using character sums.
And then this one is a generalization, I think, of what we did, André. But now the polynomials don't need to be primitive, right? Well, now this other thing here is a very interesting paper by Colbourn and others about connects a big connection with this geometry, right? That we already knew, but they did a lot of interesting things. Sets of mutually orthogonal projected and affine planes. Basically, it's a rereading of, for example, results like the one in Raaphorst in terms of geometry and properties of projected planes or affine planes. Then comes this work here that I will talk about with KIANOOSH, so I won't explain here. And I will give a preview of something that's coming up. It seems correct, and if it is, it's very exciting. KIANOOSH is my third PhD student here in the forum. So let's start with just the definition. Some of you already helped me with this, but an orthogonal array is just a combinatorial definition. It's an n by k array. It has a strength. In this case, the strength is 2. Whatever is the strength, we're going to take a set of columns of that strength, in this case 2, pick any 2 columns, and you're going to find every pair of tuples of the alphabet appearing the same number of times. In this example here, the number of times it appears is 1. So here it means every ordered pairs of elements in the alphabet will appear if you take any two powers. So here is the formal definition. By the size of the array, of course, the lambda or the index is easily found. It's n divided by b to the t-tuple. So if I have b to the t-tuples, the index is 1 and each tuple appears once, but it could be a multiple of it. Okay, so there is connections at finite fields. I have to talk about finite fields. We'll love it. So, you know, many important constructions, you know, best constructions for orthogonal arrays that give the highest number of rows for an orthogonal array come from finite fields, Bush construction, that exists one for every prime power of range T, index 1, with q plus 1 columns. For even, you can push to plus 2. And the other important one is the last one, which is an OA with higher index, but has this number of columns that we recognize from some things that we're seeing before. But q to the n minus 1. We'll talk more about this. So this was already known from Hamming, that this is an orthogonal array of range 2. So now let's move into LFSR. So you let a FQ be a finite field with Q elements, then you pick M initial values on the base field, and you have a characteristic polynomial of a sequence. The sequence is defined well in the first n positions based on the initial values, and after that you start rolling the recurrence relation that comes from the polynomial. So you see AI, the coefficient of 1 is minus 1, and so on, right? The coefficients are here, minus, right? Because this is general for any field. If it's binary, it's minus and plus is the same. Okay, so this sequence is periodic, as Kirsten had mentioned, and the list period divides q to the n minus 1, always. And then we move to M sequences, which are, the M has nothing to do with my M, which is the degree of the polynomial, but it just means maximal systems, sequences that have maximum period. So we are interested in the sequence of maximal periods. So, well, you all know what a primitive element is. It's an element that generates the multiplicative group of the field. But also, if I have an irreducible polynomial whose root is a primitive element, the polynomial is primitive. So if the polynomial that generates the sequence is primitive, then the sequence has maximum period, q to the n minus 1. And it's called an M sequence. So all the LFSR that we'll be using is M sequence, but sometimes I'll just say LFSR. So here is a primitive polynomial. Choose any values 0 and 2. Start building the sequence based on the recurrence relation, and you get sequence. And because this was primitive, I know the period is going to be q to the cube, right? Minus 1. Q is 3, so it's 26. Okay, so this is the period is matched, and then start repeating again. So there is a lot of interesting properties. Kirsten already alluded to some. They can, those that I will mention and many more can be found in this book. That's the Bible of sequences that contains chapters about sequence. Now I'll talk about the properties that I need and I would like to explore to build these arrays. First, each non-zero m tuple of FQ appears once per period as a window size m. So this means if you pick any m, let's say the polynomial degree is 3, right? So I pick every window size 3, I will see a tuple, a different tuple. When the tuple repeats, is because I'm restarting the sequence again. So if I told you the period is q to the m minus 1, of course the 0 tuple does not appear because I never have a 0 tuple in this. So In this case, it means I visited every single tuple exactly once. So you go here, and it's a way to generate all this, the 3 tuples of FQ, or M tuples of FQ. So we have that important for us. There is other cool things, for example. So this has, the period has length Q to the M minus 1. Now, divide into Q minus 1 pieces. Okay, so in this case, Q is 3, I will divide into 2 pieces. So I have these chunks. So, and I'm copying the chunks here, right? So it is known, you see in that book, that this is a multiple of this. So this is 1 times this subsequence. Multiply each element by 2, and you'll get the other slice. So if you have Q minus 1, all these chunks behave in a similar way. In particular, the pattern of zeros is identical. They line up because when I multiply a 0 by 2 or whatever, it's going to be a 0. Important property too, the part, right, that is used in some of the results. And the other thing is the two-tuple balance property. You choose a distance, okay, but I will simplify. Let's say pick distance 1. So the number of times a certain pair appear at distance 1, 10 minutes. Oh my, okay, I better accelerate. Okay, so the number of times a pair appears at a certain distance is constant. Not so constant because there are less zeros. So it's different for the tuple 0, 0, but all the other tuples appear the same number of times at any distance you pick. So Munemasa did this. Consider an array in which, for a specific k columns here, you pick a certain k. For Munemasa was less than 2m. For us, it's going to be something up to Q to the n minus 1 divided by Q minus 1. But it could be something else. Just place the element in the sequence here, A0 to AK. Then start from A1, and so on. Okay, so it is kind of a shift, but it's not cyclical, okay? Because it's not circulant, because the guy that entered here is the next, whoever it is, right? So this is an orthogonal array of strength 2. This is because of the two-tuple balance property. Okay, so if I pick any two columns, they are at a certain distance, and every tuple appears the same number of times. So it is an orthogonal array of strength 2 with a high lambda with Q to the n minus 1. And I'm doing this because I want to get to some constructions of Colbourn arrays that use it. So here is, I'm going to look at some of the properties that would be useful for us. So here you have the sequence, shift by 1, the sequence again, okay? So I'm showing the period of the sequence here. Okay, so the rest is just repeats. But even in the period here, I want to get a chunk of a slice, right? I divide by k minus 1 and just get one of those slices. Because q is equal to 2, I will get 2 slices and I'll stay with the first. So that is q to the minus 1, q minus 1. Okay, so this is actually equivalent to the construction of Hamming. It is an orthogonal array of strength 2. But it also, we know more, it has almost a strength 3 because of some ideas that came from Munemasa. Munemasa was working in F2, but anyway, it's almost a strength 3 because so some things we know here. This is an orthogonal array, right? Here I do all the 27. I have to add the row of zeros that because the triple 0, 0, 0 never appeared. It's added there. Also, very interesting thing because of this linear, this LFSR, the position of zeros here. If I look at the position of zeros and I look at the columns as points and points. Okay, so these are lines. These correspond to lines in the projective plane. The positions of zeros. So, for example, 0, 6, AB. But because of the cyclic structure, is actually one that is generated cyclically via a different set. So 06 AB plus I are all these positions. Because of the slicing, the slices being identical, right? These are the bad points. The zeros is when we don't have the coverage we want. But the second half will repeat the same zeros, so it doesn't increase the badness of the situation. And there is, if you count, there is many more tuples that are covered than not. Because we are only not covered when you have 3 columns for which you find 3 zeros on the same row. And you count that is much less than the number of tuples that are actually covered. Or in other words, I'm looking at a set of 3 columns and seeing if they are linearly dependent or not. I can also look at something shorter here, right? This, I think, we actually prove explicitly because we need it in our paper, Andrea, that actually can just take the first 3 rows generates everybody, right? All the other rows are linear combination of those. And then in the paper that Brett has with Weber, etc., I could then choose other rows to generate. And what I chose is to get the primitive, powers of the primitive, each one correspond. We knew from the sequence because the sequence is the trace of each of these elements. But if you pick the representation of that primitive that's sitting on the upper field due to the 3 over here, and pick them as a basis, this is a basis. So you use the basis 1, 0, 0, 0, 1, etc. generate the sequence. This is what some rows here, and this generate the same array. Same array modulo row permutations. So we know more compactly how to represent this as that, right? Munemasa, I won't talk too much about it. This was when we started working on this, but I think for sake of time, I will not talk too much about Munemasa, but you know, it was characteristic tool. He was looking at trinomials and looking at when trinomials do not divide trinomials to count how many of the things get covered or not. Specifically given, here is an example for m equals to 3. So 2m plus 1 rows, etc. This relates to what we were seeing before. This is the smallest example of Munemasa that matches with the smallest example of us. After this, we diverge because we're looking at different sizes for K and different fields in our case, right? But here, the only places, for example, so this is one of the arrays for us for Q equals to 2. So the only place where coverage of triples, where you don't see the strange tree, you don't see all the tuples appearing, are in these locations or the positions of 0. So 28 triples have the coverage out of 35. Only 7 don't, which are given precisely by the rows of the projection plane. Okay, so then I did more stuff on this. Now, this is our original paper, right? And this is now let's go to Core arrays. So now we're going to restrict ourselves to index 1, even though there is cover arrays with higher index than 1 that could be higher. But we want every tuple to appear on a column of the given strength. For any strength 3, I need every tuple to appear at least once. So I relax the exact property of the orthogonal array, and I'm needing coverage, right? It's a covering problem. PK, 3 rows, and you look there, you will find all the tuples of the alphabet appearing at least once. We are interested in looking at those. I think I will skip the definition, but maybe just the letters here. Strength T is this parameter. The first is the number of rows that we want to minimize because it's a covering. I don't know anymore what's the size, but we want to minimize n. Number of columns is k, and alphabet v. So we want the minimum for given parameters, strength, number of columns, and alphabet. I want the minimum number of rows that already exist. This is called the covering array number. To find constructions of covering arrays, we get upper bounds for this. So that's what we're doing here. We're going to do some upper bounds. Of those lower bound is VT, but it only matches the lower bound, and there is an orthogonal array of index 1, which is restrictive. I said this, but I think v plus 1 is a bound only for some t's. In some cases, it could be v plus 2, but very little. If I have more columns than v plus 2, I will never have an orthogonal array, and I will need more columns. These are used in software testing as illustrated by cursor. So now we're gonna use those same arrays to build subinterval arrays, a subinterval array with that number of columns. Remember, it was q cubed minus 1 divided by q minus 1. That's the q squared plus q plus 1 here. Same properties. Now, we are trying to find two polynomials. Actually, Sebastian Raaphorst, he was experimenting with different polynomials, and then we saw that there were some that worked. We stacked two of them, use one polynomial and another, and bam, we get a covering array. And then we noticed that the polynomials were reversals, among others, but the reversals always used, and then we proved. So we actually use this, and I do the same sequence for the reversal polynomial. Remove this because this doesn't have any coverage, and this is an orthogonal, it's a covering array. So what you prove that if something is not covered here, it is covered in the reversal. It's by the property of the tuples that have to do with this different set that appears here. And after you see the proof, it's not difficult. but yes, it works in general. So basically, I can build it some compact way. I can actually the reversal polynomial, which is this polynomial, right? And I invert, basically flip the coefficients around. It's the same as flipping the sequence to the other side. So it's very simple. I have this, I have the opposite, the covering array. So this was very excited then. We looked at covering array table by Colbourn. We built the record, so our name goes there, right? and that's this box, right? And it's not bad because, you know, for q plus 2, I could use q squared. But now I'm using only 2q squared, but I can square the number of columns. So that's very nice. So I will be calling this RK in honor of Sebastian Raaphorst because it is this construction that gives this bound. 10 years later, it's still for this particular parameters, right? 1 for each q out of the prime powers smaller than 23 still holds the record in covering array table. So you find Raaphorst, Stevens, and Moura is the same one. It's a very strong array, and I don't know if it's optimal, but it is very good, right? It's very short for the coverage that it has. These guys here then notice that actually what we have in this construction is two projective planes on the same points, so that they two together form a covering array, right? So what is the property? One line in one intersects a line in the other in at most 2 points, meaning that in that matrix, I will not find 3 columns in which one projected plane wrecks my coverage and the other as well. No, because if this has a 3, the other has a 2. So they don't have more than 3 columns. So they actually generalize this. You say, what about the affine planes? So they prove the things about them. They call this orthogonal. Okay. Mutually, orthogonal is not a type of projective planes, but also affine planes. They are this definition I said. So really, Raaphorst construction is 2 orthogonal projective planes. Corresponds to it. Now, how much time? 10?
Zero.
We can go on because I'm the last one. Okay, I'll be quick. This was, I had this idea that because this is so strong, maybe I could paste several copies of it and obtain a bigger one. Of course, I have to fix coverage by pasting 2 copies of this strength 3 and find something. So it was an initial problem I gave for my PhD student to see if he likes this thing. And we were trying to use different polynomials on the copies and something like this. So that was the case. Can you duplicate, put through strange 3? I know I have to add some other stuff to complete the coverage, or, several copies. So this is the loose question. And this is what we answered in our paper here, or some X's, right? So the main idea is we use the strong, nice ingredients. Basically, you use Raaphorst RQ, very strong. The strength 3 almost strength 2 almost 3, so it gives us a lot. even when you paste them together, it also gives a lot of coverage across the parts, and always given by both. Row type constructions, which is recursive, using pretty smaller ones to build bigger ones, like doing this. And we do optimizations based on the fact, in this case, Raaphorst has the property that it is a tree formed by two pieces that are two arrays, strings two. So with that, and the nice structure that comes from finite fields, we can save some rows. So with all that, this is the first result, duplication. So this is the Raaphorst size, we duplicate. See how beautiful it is. This is a bush construction, an orthogonal array of bush. Sorry, it's the product of two orthogonal arrays of bush minus some repeated rows, so very easy to do. The LFSR one, and then we have this added element. So when I do plus E, I add that element to every entry. And here is a primitive, so I add all the elements of the finite field in this way. Works. 100% finite field construction. So even if it didn't beat the record, it's good. It's not a coincidence it works, because this exists, right? This construction of putting strings 3, 1 and completing with some strings 2 using something related to what Andrea said works, right? This was done. This is, if I apply this theorem of Chateauneuf with other ingredients, this we saw a posteriori, right? When we were trying to see, what was in the tables. It would give this. But now that we know this part is an OA, we can make this part be part of the 3CA, but at the same time be one of these ingredients that I need to complete the coverage. So I start this is 0 here. So we save this number of rows. Same thing, I won't explain all, but for qutuplication, multiply by Q times. Now, Andrea, what I'm putting here is a difference covering array. Okay, we have the added array is a difference covering array. Every pair of columns, every difference appear. This is essential to complete the coverage that I need here. And because I also have, I also need to put the rows of another covering array there. All again, finite fields, everything, every ingredient certified finite fields. And then these are more complicated for Q square application and Q square plus minus Q plus 1 application. It's in the paper. We got everything that's a minus, we have a better record than the tables. It's interesting to see when we don't and what we were competing for. Of course, if something was Chateauneuf Dublin, no, that's not Chateauneuf Dublin, but something else, yes. This is one of the constructions that we just took a bit of it. Okay, I will take a bit of it, the same bit of it in this two. But in other cases, there was something better before that now, the cyclotomy was, but now our duplication is better. So it's interesting to look at this table. We don't have time to observe this. What's next? Just one slide. I already am not going to review what we're seeing, but we want string 4. We want arrays of string 4 that are formed like the several copies of strings 3. That's what we're doing with semantics, right? Long time we have been after it. It's difficult. I am cautiously saying that I think we got it. I already revised this proof twice. We're writing it, okay? So that's why I put it in brackets. But here is 3 copies. Yes, 3 copies of part of an oval, which is of this size, and it's part of an ovoid. It's half of the size of an ovoid, half, 3 parts, and then we have now. So this is generalization of Raaphorst for string 4. Very strong, verified up to Q equals 3 by computer. It does have the coverage, and we did have records after 7. So this is a very strong array. Has also connections to all ovoids in geometry. Sorry about taking too long, but that's it. Gracias a todos, and Daniel, feliz que cumple bo. Bo is how the Uruguayans say, no, bo. Okay.
Okay, so we still have a speaker from abroad. So I would ask those who have questions to Lucia to please sit next to her in the conference team. So you
You can pick up the ground there. Okay, thank you.